Thank you for coming. My name is Eduard Paulenoyu, and I'm a PhD student here at the university. Today I will talk about model-based testing. I think you've heard from Daniel and from others, I think, about model-based testing, but they didn't get into details. Yeah, so I will start first. Before what do I know about model-based testing in order to tell you something about it? So I've written programs and tested them sometimes using models, and I think most of you have done that. I'm splitting my time between Mellon University and Bombardier Transportation. I'm a tools engineer there, and I'm working on model-based testing and automated testing research. And I'm the co-author of Complete Test Tool that you used in the lab with Adnan and other tools. But today, we have until 12, and I think we'll start by talking about the overview of model-based testing, some general definitions. Then we'll go on how to model software. How do we know that our modeling approach is the way to go forward for testing? Because the models can be something very complicated, but not useful for testing. And then we'll discuss some strategy on how to generate tests using these models. Then I think we'll have a break, hopefully. I'll try to make it at 11 to have a break of 50 minutes, if that's okay with you. And then we try to execute those tests generated using models, and then we'll just have some summary and conclusions. No textbooks for this class, but I have books that I like, so I usually recommend. So it's important to say that the Practice of Programming, this one, by Kernighan and Pike, I like it, and they have some things that they don't call model-based testing, but they're very related to model-based testing. Then a practical model-based testing book, A Tools Approach by Utting and Bruno Legard, and it's this book. I think you can get it from the library also. I had it from the library here. Then I think you know the book Software Testing and Analysis that's recommended for this course by Petse and Young. Try chapter 14 if you didn't try it right now before. And I like it myself, and it's recommended by colleagues who taught classes on testing, and they really like it. Yeah, so let's go forward with this. So overview of model-based testing. Basically, we need to define what is model-based testing, and if you look at the words that contain those the words, then you specifically know what we're talking about. But what I'm referring is that you run a program based on a specification, and this can be a model, and in order to find faults, aka defects, errors, flaws, bugs, you can have a lot of definitions of model-based testing. But this one I like a lot. And why we're actually using model-based testing. So we saw that there is model-based testing was proposed 25 years ago. And it was used in practice. It was used now it's used in Visual Studio and other in other tools that you can perform model-based. So we saw that you have better tests. Basically, you can have better tests at detecting faults. It's a lower cost, so you try to model some parts of your system, you generate tests. This is done mostly automatic. So the cost of actually producing tests, of having real testers doing that work and not supervising the model-based testing approach. So this actually reduces the number of man hours that you have in a company or when you're working. So you actually have early detection of requirement errors. So we have studies that show that. And basically what we saw that people started earlier in the development process by using models and generating tests automatically, even if they don't have the system under test, so they don't have the implementation, still they try to generate them, and that brings some knowledge. You also have traceability. So basically, if you have a model where you generate tests, that's actually like a specification that you don't need to write. You write it once, and you have a version of it. So basically, you can trace how the model evolves over time, and also tests that come from that model. Automation, that's an important part. So basically, model-based testing is good if you do it automatically. If you don't do it automatically, then it's something wrong, and that will not actually bring that much benefit to your process. And it's, I think that's quite, in 2012, some researchers actually showed that model-based testing shows less overlap among tests. So basically, you don't have a lot of tests doing the same thing, but you can have some tests doing testing some part of the system, and then you have a lot of tests doing some other parts of the system. So you can actually have less overlap among tests. But yeah, let's go further. It could be boring to talk about that. So we'll go for the process. What's the process of model-based testing? So I just devised a quick process for this. And basically, you start with a model, and that comes from the requirements, that comes from the specification. Maybe you have something like that you generate automatically models, or you build them yourself. And then you have a specific criterion that you want to fulfill. Based on this, you have a test requirement, so you devise a test requirement. And you use this to generate abstract tests, meaning they're tests that cannot be executed because they're coming from a model that is very, very abstract. So you don't have everything you need, the harness to actually execute them. So what you need is some glue information that I called. That is basically information from the code that you need to actually hooked in. And also test oracle here. And the test oracle is something that says the expected output or the expected values that you want to have. And this can be that can come from the model, but you can have it also separate. And that forms the executable test. And then you can run it on the actual system, and then you can have a report on it. And there is a lot of research and tools for this, especially for criterion, how many criterions or what types of criterion to use. Creating models, there are a lot of models out there, and how to execute tests. And there is not that much information on how to do this in a general way to get from abstract test cases to executable tests. But there are some approaches to that. So yeah, I just want to stop a little bit now. So if you have questions, just raise your hand, and we can just stop, and I can stop and answer your question. No questions. That's not good. Yeah. Modeling software. So basically, I think you know. So what is a model? I think you use models somehow. You know about models. What models did you use? Do you know? UML. Yeah, that's perfect. I mean, when you use UML, you use it not for generating tests, but just for documenting, I guess. That's a good example. Do you know other examples of models? Spam?
Do you also use for modeling?
Okay. Yeah. Yeah, I understood something else. So that was like, yeah, that's okay. I never heard about it, so that could be. ADL, that's an example, yeah. That's cool. I mean, there are different type of models, and you can think about Simulink and other type of models. But basically, you have it's an abstract representation of a system that highlights some properties of interest. So basically, you have some unnecessary details that are removed. You don't need them for your test generation purpose. If you start from code, you'll have all the properties and all the problems that come from that. You highlight the subject of interest, so you deal with complexity in a way. And this improves sometimes. It facilitates studying and understanding of the system. So you usually do that in a mental picture. You basically you look at the system, what should you do, and then you draw it or something in your mind. And that's a simplified version. You don't think about all the characteristics. And I'll give some examples of models. This is not actually a software model, but let's go for this. So you have a castle, and the model of a castle is like a map. So you have a map of a castle where it shows you where you are, where is the garden and stuff like that. So that's a useful model that we usually use when we visit that castle or something else. Yeah, I think I like the next one. So this is the model of an actor. So I like Harrison Ford, and the model omits some details. So in this version, the Lego version, the simplifications is relevant, but you have a lot of loss of information. But it looks cool, I would say. Yeah. So not all models are very useful. So we're trying to have useful models, especially in software engineering. And they need to be abstract. In a way, they need to emphasize the important aspects while you remove the other ones. And then it should be understandable. If I show you a model, you should be able to understand it quickly. Otherwise, it's not useful. It should be accurate. In a way, it should represent the model of the system, of your software, or your requirements. And it should be predictive. That can be used to answer questions about the models of the system. So basically, in time, you need to predict stuff about it. And it should be inexpensive, so it should be easy to actually build it. It's cheaper to construct, study. And I will start with a simple model, like a definition. So you know a graph, and I will just go quickly through this. A graph G here is a model composed on nodes and edges, and or called arcs. And these arcs are connecting these nodes. So graphs represent relationships between objects for which the nodes stand. This is something that you studied quite a lot, I guess, before coming here. And you can actually have labels on these models, so you can put an identifier that names the elements of the graph. So the edge from A to B, in this case, is labeled with A. Another important definition, before going into useful models for software, is a path. What is a path? And it's a sequence of edges such that any two edges that are close to each other in the sequence share a common node. So here you have from A to C to D to F to E, and then you go back to D. So you have a common node. So that's a path in your graph. And most of the models that I know are based on this type of graph. So you can have structural models like UML, and you can have UML class diagrams, you have UML state charts. You can have finite state automata, finite state machines, control models like MATLAB, Simulink. They're all based on some type of graph theory. Function block diagrams that you used in the lab. And also you can have timing models. So basically you encapsulate some timing information in it. But we use it usually in maps. So we try to have models of maps. So Google Maps uses a lot of models. So they have a lot of model-driven engineering there in their development, where they actually have, they don't have all the information about the map. So they actually try to abstract it a little bit to show it to you. Also, you have traffic system dependencies. There are a lot of models on how to regulate this. And computer networks, yeah. So in computer networks, you can always have something like a model. And there are other examples, but I'll not go through them. Other way to look at the model as a graph, it's like if you remember about state machines, and I think you've heard about them. And a state in the state machine is an abstraction of those variables of a software system. So you try to encapsulate in a state and in a state machine how your software works. So in particular, in a state machine, a state can be applied, can define a user input, or the inputs that can be applied by the user to get to that software in that state. And that could mean the manner in which the input influences the output or influence a local state. And basically you can have a more representative model of state machine. That's a finite state machine that we can use usually in reality. And a finite state machine is an abstract mathematical structure that you heard about, I hope, and that is composed of a finite set of states, a finite set of inputs, and you have a complete definition of this mapping between transitions from one state to another. What you need to know here is one of these states is the initial state. So you start from the initial state, and a state machine, and then you have a number of designated final states. And the machine terminates successfully if you're in a final state. But this is, I think, too much theory, so let's go for some example. So I have here a requirement of a light switch. So if a user quickly presses the light control twice, then the light should get brighter. On the other hand, if the user slowly presses the light control twice, the light should turn off. So I actually made a simple state machine, finite state machine for this, where you have 3 states and 4 edges. So basically the light switch can be in 3 states: off, light, and bright. So if you press twice, you get in bright. If you press twice like this, you go to off. If you press twice and then you press again, you go to off state. My question, what do you think about this model? Did it capture the desired requirements? No. Okay, why?
Because you have to press fast, and that doesn't say in the model.
Okay, so how do you have this is a good point, and I think you can take like 30 seconds, 1 minute to think about what do we need to put on this model. You don't need any mathematical, I mean the mathematical concepts that you know for now, it's enough. That's a quite a good point. So how do you implement the clock? What do you mean? So how do you use it in this model?
You start with 0, yes, and then after some action, you start the clock, and if that clock reaches some state, you know, 5 seconds, and something is not pressed again, like this for the bright, then you don't have anything. It will return to off state. But if you press clock twice in amount of 5 seconds, 10 or something like that, then it will change to the bright side.
Yeah, I mean that could be a solution. Do we have other solutions? I can show you my solution. It's very similar to what you said. So basically the solution is to have a clock. And what I do is when you go from the state off to state light, you make that clock 0. So you start fresh. And then basically when you're in light location, the time is progressing. So if you press the button again in this interval, you go to bright. If you don't do that, you go to off. So this is really simple, a simple model that works to represent that requirement. Is it okay? Do you understand? There are complicated models than this, but I think the requirement is actually quite simple. So I will go to strategies for generating tests using this kind of models. So I didn't state that much into how to model, but now you have just a flavor on how you try to model these requirements. Basically, I want to go to the big picture now, and testing. We're in the software testing course, so even if you talk about models, you need to go back and to see what's the purpose of testing. And I think in my mind, testing is almost an attempt to cover something. So you cover some measure of a structure, or you cover some nodes of a graph, like in the light switch example, or inputs that give different outputs. So you try to look just at the input space. You can actually go for all possible inputs, but that will not help you that much, because that's generating all possible inputs is undecidable. So if you solve that, that's quite impressive. Then you can actually look at covering the logical expressions in a model. And then you can actually look at the pairs of variables that are defined and used. And this is definition use coverage criteria. But usually we cannot guarantee that coverage directly correlates to more bugs found. And this is interesting results we had empirical studies related to that show that even if you have some type of you cover some type of structure, that will not actually give you more that will find more bugs. So maybe you need techniques that are tailored to that. But still, I mean, everyone is using that, and especially in industry. So how do we go from models to test keys, having this in mind? So we have the specification of the light control model that we did together, I would say. So we didn't do any other model. And then we have the software implementation of it. Or you have a software, you can actually have it directly in hardware, but I would like to have it in software now. So you have, the inputs are press, so the button, and the output state will actually give you the light. So the requirement, one of the requirements could be check that the light can become bright. So that's your test strategy. So when a test case would be that you press the input, and then the output will be light at time 0. And then you press again very fast until 3 seconds, and then you'll get into bright location. So this is a simple case. Then you can try to cover this final state machine. So you have state coverage. So every state in the model should be visited at least once. So a test that will cover this, that will actually have state coverage, will be to go to off, to go to light, to go to bright location. And transition coverage is another type of measure where every transition between states should be traversed by at least one test case. These are very useful type of coverage, and we will use them further into today's lecture. But there are some strategies on how to search through this model. So you don't want to do it manually as I did it now, because you have a simple model. But you need to actually look on bigger models of the software or of the requirements. And usually when you're exploring lots of executions, that's called random testing. So you just random testing or search-based testing. So you basically execute the system quite a lot in order to measure something. You can do it randomly, so basically you generate inputs. And that's really quite useful. There are companies using random testing, including Microsoft and Google. Every day they use random testing, and they detect 50% of the bugs using random testing, which is quite good. Then model-based testing can focus on exploring lots of paths, and that's called concolic testing. And this is something that only researchers do for some reason. And then if you explore states, maybe you know the term is called model checking. So basically, when you try to explore lots of states, you have a special technique that was devised 20 years ago and got the Turing Prize. So a model checker is a tool for exploring a state space. And I will try just to show you that model-based testing using model checking is something really, really useful. that is used in industry nowadays quite often. And the basic idea is to generate every reachable state of a transition system or of a finite state machine. So you can think of states as nodes in the graphs, and you have then directed edges. That means from this state, it is possible to go to the next state of the program. And then you can have multiple outgoing edges. So from one node, you can go to one state, but you can go to another state. So this actually complicates things, but you can have non-determinism there. And we will look at one particular kind of model checking, and that's using UPAL. And that's a tool for model checking. And we will explore the state space of programs. But you have other model checkers. So there's SPIN for C programs. That was used for checking all the code in the Mars rover, the latest Mars rover that was sent. So basically, all the code in the Mars rover is C, not Java or other languages. And it was actually model checked with SPIN. Java Pathfinder 2 from NASA Ames. That's another model checker for Java programs. So basically, you can model check any type of Java programs you have. And also Bogor. This is not very useful, but yeah. It's from University of Kansas, Nebraska, and it's used in research. To give you just a simple example of how model checking is useful for generating tests on finite state machines, I can actually, we'll call it this a control flow graph, because you know what's a control flow graph, and it's very simple. You have nodes and directed edges. Basically, model check is executing all states in the program, and it backtracks. So if you go from the first state, you visit the second state, and then you actually go back here. And then you go again, and then you came in the same place here. Then the model checker will say, oops, okay, so the state is already visited. Backtrack and try a different operation. So you go back and you try a different one. And then a different one. And then, oh, done with the test. So you came here, but you want to go to others to explore other states to see what happens. So you backtrack and try a different operation. Then that's the state is already visited. So you backtrack and try a different operation. So basically, in this way, you will try to explore as a side effect. You'll have as a side effect many executions, many paths. But we are trying just to explore states. And that's a useful technique when trying to actually generate tests for this kind of finite state machine. This will actually make your life easier. 25 years ago, we didn't know how to generate tests efficiently for this kind of models. But now we have the tools to do that because of model checking. But let's do an exercise. And I think you were really close to, for some reason, to the break, so in 15 minutes. But I will explain it, I think, in 10 minutes. This is an example of testing. I call it mission scenarios in a video game. But it's just, if you heard about the problem Viking crossing a bridge problem, then you know that this is very related to that. So basically you have four Vikings. And why are they crossed with this kind of blue, I don't know how to call them. Basically they have four numbers. And this is 5, 10, 20, and 25. And basically the Vikings are about to cross a damaged bridge in the middle of the night. So the bridge can only carry 2 Vikings at a time. And to find the way over the bridge, the Vikings need to bring a torch. I didn't design this good. So if you look, it's very, very poor design here. Game design also. And the Vikings need 5, 10, 20, and 25 minutes one way to cross the bridge. That's why they have numbers on top. because they're injured somehow, so they need more time. So the healthiest one can take 5 minutes to cross the bridge. So every Viking takes a different time to cross the bridge, so one Viking can be faster than the other. The bridge can carry, I said, only 2 Vikings at the same time. So Vikings needs to get the torch, and they have only one, so you don't have multiple torches. My question is, and I think you see it there, can the Vikings get this safe in the safe zone here on the safe side within 60 minutes? Can you actually show me a test of a schedule which gets all 4 Vikings over the bridge within 60 minutes? So I guess if you Googled it, you got the solution, I guess, or you made it yourself. So what kind of solutions do you have for this? So is it possible to find a schedule that all 4 Vikings could reach safe in 60 minutes? What? No. We have a no, we have a yes. That's quite good. I want to hear a I don't know. That's the best. So you said yes, you say no. Why no? Why not?
Because it's basic addition. If there's one torch, so someone need to carry it and 2 can go at one time. So you begin with the 25 and 5 go over, the 5-1 carrying the torch, and then when he gets over, the 5-1 runs back, and then he goes with the 20, goes back, and then he goes together with the 10, and that adds up to 65 minutes.
That's so you showed me a test when this is not possible.
Yeah, I tried to do the fastest one.
So you didn't actually prove it in a way, yeah. So you say this is not possible. But you think if you have a test that shows that it's over 65, then it's not possible.
Yes.
There is another solution? Better solution? Do you think?
I think it's possible, but I'm sure it's possible, but I don't know how to.
Oh, okay. Yeah. Someone said yes, so you said it.
Yes, maybe I made a mistake, but I found a solution how to cross the bridge in 60 minutes.
You want to throw it?
Yes.
Yep. This is slow.
Yes. So we have one state and all guys are on the left side.
Yeah.
So we cross. So 1 and 2 will cross the bridge, so it will take us 10 minutes.
Yeah.
Then we return this guy. So the state is 1, 3, 4, and it takes us 15 minutes.
Yep.
Then we cross the bridge with these two guys. So that takes us 40 minutes in total. And now we go back with this guy.
40 minutes? Yeah, in total. Yeah, that's yeah.
So it is like, and it's 50 minutes.
Mm-hmm.
And then we cross with all of them. And it's 60 minutes.
Yep. That's good. Congrats. This is quite good. I mean, that's how you do it. Okay. Okay. So that's this a solution, and yeah, I will show my solution, but it's I think that it's the same solution. So basically, you have two state. You have an unsafe part and a safe part. I actually liked it when you had states and transitions. That was quite easy to follow. So basically, you go first with the Vikings that cross with 5 and 10. So that takes you 10 minutes. Then you go back with 1. So that takes 10 minutes. I went with this one that has 10. And then I'll go back. I'll go to the safe part with 20 and 25, so that takes 25. Then I go back with the one that the healthiest one. I'll go back, so that takes 5 minutes. And then I take the remaining. So if you calculate, it's 60. The red one. So basically, you need to be a little bit smart on how you cross this. You need to cross these two together, otherwise it's quite you cannot do it. These two.
Even if you go with oh yeah, now I see. Now
Yeah.
Very bad.
But this is quite good, and I mean you tried to do you did a mental picture, and it was a state machine because you've thought about that. But you can do that automatically now. Sorry for this. So I can show you I actually implemented it. So let's see how we do this. Duplicate. So I have a model checker open. Is it visible? Yeah. So I call it soldier, but so I have unsafe state. It will take, this is a synchronization because this is the torch. So I model the torch is 1, so it can be free, or so it can be taken or not taken. Basically, you don't have to care that much about the syntax, but basically it's a finite state machine where you release or take the torch. And the soldier can take it here and then release it. And then we calculate also time. So you can simulate that, like I can reset. So the Viking, let's see. Yeah, the Viking can take some torches. But we can verify this. So I wrote a property. Show me, this one, there's the symbol, there exists a path. Oh, this is quite small. Okay, so I just want to check if there exists a path, if Viking 1 is in the safe part, and Viking 2 is the safe part, and Viking 3 is the safe, and Viking 4 is safe. And I can actually check that property. And let's see, it took 65. So this is quite, we need better. So I will try to do it to get the fastest test. The property is satisfied, 60. So basically by just building a finite state machine and using a model checker, I can verify this kind of properties and even generate tests because I have everything here, a simulation trace that I can export. That shows that all Vikings can be safe in 60 minutes. But you can do it like really fast in 15 minutes, I guess, 10 minutes, or you had it faster, the solution. So you can do it either way. But I guess it's better to do it automatically. Cool. Let's go. Let's see. Oh, it doesn't work. What the hell? So now we want to actually execute tests that come from this kind of models. So this is I can show you how the architecture of a model-based testing tool looks like. So basically you have a model that you saw how it looks like, a finite state machine, and you have a test generator tool that can be model checker or random test, or doesn't matter what. So you generate these tests that cannot be executed, but then you have a test execution tool like that takes that test and puts a lot of glue code and a mapping in order to have a driver to the implementation, so you can hook into the software. And based on running this into the implementation, you have a pass or fail verdict, or you can have also an unconclusive verdict where you don't know if it's pass or fail, but mainly it's pass or fail. And the implementation usually and the model have a relationship. So you saw that we created the model based on the requirement, but you have to create the code. So you create the code by hand. So there is an implementation relationship between the model and the code. And this is called conformance. And this was studied quite a lot. And basically it means that the behavior of the implementation complies to that of the specification. So if the model is as thorough as it has the same artifacts as the implementation, then you get the same problems. You cannot actually generate tests that are usable. So the model needs to be a little bit more abstract, because otherwise if you search through the implementation, you will run out of memory quite fast, even if you have just, I don't know, 50 booleans in a program, and that should be quite simple. But that's 2 to the power of 50 combination that the tools should take care of. And we use the system model and this test purpose using this test generator, and we generate a trace from the program, which can be some random, shortest, fastest. I showed you in the tool how I get the fastest, and I think some. So I will do an exercise, so you will not have to do anything. So that's good. But I will show you Yggdrasil, which is a test case generation feature of UPAL model checker, and I will explain models-based testing by developing. I don't think I have to develop, but I developed and test a simple LAMP system with on-off capabilities. So I should write a model decorated with test code. Then you have a correct implementation of the system, or what I think is correct. And the system will be implemented in Java. And I will have some execution scripts. But to explain what I will do, it's like I will create a system model and a user model. Basically, the system model goes from off state to on state, and from on state to off state. This is quite simple, but I wanted to keep it simple for you to understand this example quite fast. And then the user model, which takes the button clicking. So basically you would go to on state or off. If you don't know, maybe I didn't explain that. So there are this question mark and exclamation mark here. Basically these are just synchronization. So I have 2 finite state machine. When I take this transition from off to on, this will synchronize with this one, with the same name. So it will take the transition in the same time. So I want to, you can have multiple finite state machines working in the same time. And then I implement, you can implement an app for that, a class. I call it app, but yeah. And then you have a couple of methods, set on, set off. So you can go to on state, you can go to off state, and then I have some assertion. So you expect to be in state on, to expect to state off. Then I will use the test generator to generate some executable tests, and then I will run it on the code. So basically, I'll run it on this app, and then I'll have a pass or fail verdict. And I will do it live. Let's see if it works. Two. So So I implemented this. So you saw this model that I showed. I think I need to do the resolution to be smaller. Okay, I'll go for this. Okay. Is it better? Yeah, so this is the UPAL tool. You can model your system in a final state machine. So basically it's 2 states off and on with 2 transition. Every transition has these synchronization channels where you synchronize with the user. Basically that's it. You can simulate this so you can see how it works. But what we want now is to yeah, so I can verify this if this one says that if there exists a path, if the process, if the lamp is on, which is a quite simple test. And you can select it, and I can generate first, and I can look to see if you can, even for this simple test, you have 100% location coverage. You can see here. And edges, you have 50% of them. And 71% trace quality. This is, I actually don't know what this is. But then we can generate the executable test. And I will show it to you because I reload it here. So basically this is what class test extends app, and then you expect off, you set on, expect on. And this is the implementation of the class that we want to test. Let's run it. I have a bat folder for that. Okay, so the test runs successfully. This is quite good. But then maybe we want something more than what I verified. So I just want depth search. So basically I will just go 20 iterations into the program, just randomly, give me some things. So I will generate, it went 20 steps. You have 100% location coverage, 100% edge coverage, and I will generate the output. And this one will be bigger, I guess. So there are a lot of combination of set off, expect off, set on, expect on. So basically you just try to call the method, see if that happens. This is what it does. And if we run this test again, test runs successfully. So basically with this test, you see that your implementation is correct and you generate the test automatically. You can really do more complex programs, but I just wanted to show you this simple app because it was a simple class, because it's simple to actually look like on these methods. Let's go back. Okay. So I showed you an example of how to generate tests, but also execute them. So it's quite easy to execute tests using a model checker and using model-based testing. But I want to make a little bit of a modification to the exercise, meaning you will use a little bit of mutation testing. So you heard about mutation testing until now? Okay, so this is, maybe someone needs to tell you about that in the next lectures, but I don't remember. But mutation testing is used to design new tests and evaluate the quality of existing tests. So it involves modifying the program in small ways. And it was devised in 1978 by DeMillo and Lipton, not the T, but another Lipton. Each mutated version of the program is called a mutant. And the test detects or rejects the mutant by causing the behavior of the original program to differ from the mutant. So basically you do a small modification in the program, you generate tests for it and see if the output of the or the steps in the program differ. So this is killing the mutant. So a test that is killing the mutant it's a test better than what you had before. So the purpose in this is to help developer develop effective tests or locate weaknesses. So a test that will detect more mutants is a better test than the one that doesn't detect that. And this has shown that it's better than coverage-based testing. So if I wanted to show you this in the same example, show you how you can actually detect bugs in the program. So I will use the same approach, and I will make a mod. I have a mutant with an implementation error, and I have the mutant is implemented also in Java, and I will execute the scripts. But basically what we do now here is having the same model, the same final state machine. We have the implemented model, then we create, we mutate it, so we have a difference here. And the difference is that when you set the state off, you don't do anything. So basically, you're still in state on. So we need to actually have tests that are better to detect this change, because if someone didn't implement the specification correctly and did this implementation for some reason, then the test should detect that automatically. So we'll execute the test that we had on this program to see what happens. That makes sense? Okay. So I'll go again. A lot of sitting in this lecture. So, okay, I can show you the mutated version. So what I did is this is the correct implementation, and I just commented this one, state equals off. So the state, what? Sorry. Wow, that's quite good. I was explaining something without showing it. Okay, so this is the correct implementation. You see here that when you want to set on, the state becomes on. When you set off, the state becomes off. The mutated version is like this. So when you set off, the state is not off. It stays on. And that's the only thing that I changed. So I will try to use the query file, this one, that a test that will show me that the light switch will be on. That's it. So I will generate a test for that one. Output, see the test case, and execute it on the mutant. It actually worked. So it didn't detect anything. And this is quite obvious why, because we just check if he's going to on, and that's it. So it will take this transition here. That's it. So it's a small test that will actually not detect this bug in a way. But if we go for a longer test, the one that I showed before with a depth search of 20, basically we just randomly go and to see what are the 20 steps into the program. We generate this. This is actually longer. And then we execute it. Okay. So we have an assertion error, of course. So we know where the bug is. Basically, we just mutated the program and then executed automatically this. You could see that having a lot of mutants in your program, then try to execute tests. The test that will kill more mutants or show you some assertion errors will be better than tests that will not show that.
But if it's an error, does that mean it's a real error?
Yeah, of course, that's a real problem. So basically, you mutated the program, and you assume that could be a real error. Yeah, that's what your question is, and that the mutant actually is not an error, maybe, or not. Can you say it again?
I mean, so the point of like mutating, is that to discover error, or is it to discover if the program discovers the mutant error?
No, it's the test, if the test discovers error. Yeah. So a test that will actually show you that, that will show an error in this program will be better than a test that don't. So there is a relationship between actual mutants and actual errors.
But how do you interpret it?
Oh, the result here.
Maybe you have to do that.
No. I mean, I will do that. I think in the next couple of slides, but because I don't think I will work on that. But you can see here that when you execute in the same test on the mutant class, you will have a fail verdict here, yeah? And if you run the same test on this one, this will run like usual. So if for some reason you don't have, if the developer didn't implement it like this, and he started and implemented like this, for some reason, then by running this test that I showed you and seeing that it fails, you could detect that error. So having tests that will detect the errors on this kind of mutants will actually be better when actually implementing.
So this is basically a way to see if test is good, if it can detect simple faults, and if it can detect simple faults, it
detects also complicated faults.
It could detect faults in the original one too.
Exactly. So that's an assumption. It's called capable programmer assumption. Basically, we make the assumption that small changes in the program will actually reflect also bigger changes in the program. Basically, a test that will detect small changes in the program will detect also bigger. And we have a lot of research that was done in this on this, and that showed that mutants can be used as faults, real faults.
So we test the test and not test the program?
No, yeah, you test the test. Okay. It's cool. And if you use it with model-based testing, it works quite well because everything is automated. Yep. So I actually have, I don't think I have that much material left. So I have a home assignment, but this is optional because I cannot actually put you to do this some way, except if you like to use this tool that I showed you today. So you can download the Windows, Linux and Mac version, 4.1.19. That's the latest version from upal.org. And you can extend the lamp switch that I showed you there. And I have the template. And you can find also the template with the tool, such that it works like follows, like this one. Or you can do a better version. You can add time. It depends on you. You can do it like this, or you can add time to the final state machine. You can implement it in Java using the template that I used, and you can generate executable tests, as I showed you in this lecture. And the video of this lecture will actually be available in a couple of days. Let's see. And you can use a depth search and a depth of 20 to generate tests, but also to use a test property. So generate the test when the lamp becomes bright, to see what happens. And I would really like to see if you can use also mutation, because the mutation can be really useful when using model-based testing. So I'll just go further to summary and conclusions. So this was quite basic here. So I showed you a lot of demos and a lot of things that are in that you can find, you can do yourself. The advantages, as you see, is that even if you generate test suites and tests that are large, they're sometimes better. And by using model-based testing, you can actually generate automatically complicated input test sequences or sequences of tests. And you're likely to expose failures like that caused by the weird combination of inputs or weird combinations. And you can provide an additional basis for coverage-based evaluation of your test progress. And you can measure the quality of your product. A model is a precise communication tool. So when you show a final state machine to any other person, it will understand the same in the same way. So it's a good vehicle for presentation, to also to non-technical stuff. And while you build the model, I think you did today in the break, some of you, you develop a better understanding of the system under test. And you find sometimes bugs just by building the model. And you also can compare different versions of your product by having these models. Choosing models to fit needs. Now it's like, oh, it depends what application you're building. So there are models for HTML processing component in a browser, like you have calculator mathematical expression, you have a different model for that. So if you want for this one, it's better to use models like Simulink and function block diagrams. Then if you have a GUI and phone system, it's better to have just a simple finite state machine, because this can become very complicated in the number of states. So basically, you have different models for different aspects, and the combination of models are mostly useful. As you saw at the beginning, we had the model of the lamp without time, and that was a stupid model. You don't want to test from that, based on that requirement. So we added time, and the model became powerful. So a combination of models is sometimes useful. Sometimes it's good we don't have sometimes you build models by hand or build it by yourself, but sometimes you use from design requirements analysis or from actual code, you generate a model. So you can use that model. And I would recommend you to try the following tools if you want to try more on model-based testing. Yeah, I recommend you already UPAL, that is used for embedded systems. So it's used by ABB, Bombardier, and it's free to use for academics, and has support for model-based testing of Java code. So if you work on Java code, then you can use UPAL. If you like C# instead, you can use Spec Explorer. And the Spec Explorer was developed by Microsoft. And I think the latest version is publicly available, is from 2010. But they have some really cool features. And it's part of Visual Studio Power Tools. And now, I think in 2005, there were 100 testers using it on a daily basis in Microsoft. That's not that much, but we don't have any data after 2005, but we know for sure that a lot of people are using model-based testing. You saw complete test, and you use it in the lab for automatically generating tests. That's used in Bombardier, and that's also based on model-based testing theory. Then there is another model checker here that is used for verifying kernels. So basically, you can take the Linux kernel and try to verify a lot of properties there. So even if you have 1 million lines of code. I cannot, COQ, I don't want to pronounce it. So I don't know who, I think there are some French people that named it like that, but yeah. But it's really cool to use, if you use this one for if you have large quantities of code. So yeah, thank you, and that's it. Thank you for today.